Alright, welcome to 8.3, the normal discrete approximation. So we talked a little bit about normal distribution yesterday. So one of the applications of the normal distribution is that we can actually use it to approximate discrete values and iterations. Okay. So we have our normal distribution we talked about yesterday, discrete data, so things that we're counting that are wholes or intervals, and then a normal approximation. So sometimes the sample of data study is taken from an underlying population that is distributed normally. In such cases, we can choose from the sample population also be normal distribution, normally distributed. So if it's normal here, our sample should be normal there. Okay. For example, farmer Appleby has a large apple orchard in his farm. He finds the mass of the yields amount of apples in kilograms for each tree of 20 trees in his orchard. There they are. Use little magic, and there's the mean, standard deviation. So the mean is 9.8, and the standard deviation is 3.3. Given the mass of the apples is normally distributed, determine the probability that a tree selected at random from the orchard has a yield greater than 11.5 kilograms. So again, we can use our norm CDF, just like we did yesterday, and we get that there's about 68% probability that the tree will have greater, actually in this case, less than 11.5 kilograms. So if you want greater than, we'd also subtract that from 1. So actually, in reality, it would be about 32% probability that the tree would yield more than 11.5 kilograms. My mistake. I guess I made a mistake when I was entering the data. We can see how the normal CDF works from yesterday. So, normal models for discrete data. So, we've used continuous data so far, the volume of kilograms, so kilograms changes into continuous value, time, anything like that. So now we want to look at how that works with discrete data. So we can sometimes discrete data also model normal distribution. So if we looked at the discrete binomial distribution, probability distribution, or the discrete hypergeometric probability distribution, and you graph them, you'll notice that they actually do kind of lead into what would look like a normal distribution curve, or bell curve. Two things have to apply. One, the set of data has to be reasonably large. What that means really kind of comes down to interpreting what your data is, and then looking for a large set of data. And of course, it has to be symmetrical and have only one mode, giving you the bell shape on the graph. Okay, so how does this really work? So say we had 100 trials of something. So we could kind of do a frequency table, and if it was normally distributed, we get something like this. And we can draw a curve by joining the midpoints of all the points, all the frequency bars, and we get something like that. So if we do 400 trials, you can see that the curve is getting closer and closer to being nice and smooth. Do 900 trials, and you can see that the curve is just nice and smooth. There's so many trials that we joining the midpoints of each of the frequency tables really is starting to become continuous. We can't really distinguish one interval from the other. Okay. So it's very close to being distributed. So, how does this work? Okay, so say you own a jelly bean factory and you're packaging your jelly beans, and you want to make sure that the jelly beans have the appropriate number of jelly beans in each bag. You don't want to shortchange people or overindulge, because that's just wasting your money and giving people more jelly beans. So if the number of jelly beans in the package is normally distributed with a mean of 50 and a standard deviation of 3.2, what is the probability of getting 55 jelly beans in a package? So as we said, this is normally distributed. We either use the table method or use a calculator method. I'm going to use the calculator method just because the interval works a little bit better. So here we have the norm CDF again, 54.5 to 55.5. 50 is your mean, 3.2 is your standard deviation, so that gives us about 3.6% probability that the packaged jelly beans will have more than exactly 55 jelly beans in it. Not a lot. You have less than 45 jelly beans in a package. Okay, again we have our norm CDF using negative infinity, 45.5, 50, 3.2 gives us probably about 7.89, 7.8% probability. So a little bit larger, but not much. Okay, so now you're asking, what's with this 0.5 stuff? Well, what is with this 0.5 stuff? If we look, so because we're looking at discrete values, right? So 55 jelly beans, and we're trying to use continuous values to do that. If we look at the properties of rounding, you can see that there is an interval that would round to 55. So we have to really kind of consider all those values. And that's why we use the 0.5. So it kind of gives us that boundary. Gives us that boundary between the 2 points. And there we go. So there's your homework. Try it some tonight, and we'll see you tomorrow. Bye.